So, we shall continue with the long term solar energy system performance methods, the simplified design methods. Last time we have discussed the F chart method based upon air as the working fluid, which correlates the solar load fraction in terms of two non-dimensional parameters, the non-dimensional absorbed energy and the non-dimensional collector loss. Similarly, if the collector is a liquid based, in general it is water, but sometimes antifreeze solutions are added and even high capacity thermal capacity fluids are also being used and some of the oils. And however, this correlation is valid for liquid based systems. The methodology of developing the correlation is the same. A large number of simulations have been conducted depending upon a different number of locations in a good range of parameters, and the monthly solar load fraction for liquid based collectors has been related to y and x as following. So, you will notice the remarkable similarity of the correlation of the liquid based systems to that of the correlation for the air based systems, which is not surprising. So, they give comparable performance, except when this x and y are a bit too large, either because of a non-standard storage or non-standard flow rate, etcetera, etcetera. However, the slight difference comes in the air and liquid based systems, mainly because of the storage and the heat exchanger effect. In addition, you will find that the liquid based systems have certain volume of water like 75 liters per square meter of the collector area as the standard storage. So, apart from the pressure drop and the pumping power requirements, for a given x and y, it appears that they will give more or less the same solar load fraction, but the real question is, will the air collector and the water collector have similar FRUL and FR tau alpha for a given cost. In general, liquid systems have better values of these two parameters that characterize a collector, FRUL and FR tau alpha. So, ranges of the parameters are the same. However, I shall repeat 0.6 less than or equal to the normal transmittance absorptance product less than 0.9, and this area heat removal factor product is within the limits of 5 to 120 meter square, and the overall loss coefficient is between 2.1 to 8.3 watts per meter square degree C, and beta is 30 degrees less than beta less than 90 degrees. And the building loss coefficient, which we discussed yesterday in detail, is in the limits 83 to 667. So, this when multiplies the degree days will give you the space heating load directly. So, we shall recall x and y are identically defined. The non-dimensional collector loss is FR UL times 100 minus the monthly average daily temperature T A bar into delta tau, the number of seconds in the month, by multiplied by the area of the collector by the load. Similarly, y the non-dimensional absorbed energy is FR multiplied by transmittance absorptance product average for the month into tilted radiation monthly average daily multiplied by the number of days in the month and the area of the collector upon the load. Of course, FR is the heat removal factor, and tau alpha bar is the monthly average transmittance absorptance product. I should write. Of course, UL is the overall heat loss coefficient, TA bar is the monthly average daily temperature, AC is the collector area, and these are all we have written in detail in the last lecture. So, I am not repeating. N is the number of days. This is one reason I write them or rewrite them at times is we are using the same notation consistently. It will be easy for you to remember and check the consistency of the equations. H T bar is the monthly average daily radiation in the tilted surface, and L is the load in joules on the system. So, now we have spent in calculating tau alpha bar, H T bar, UL, FR, right. Of course, from the collector test you can get FR UL and nearly FR tau alpha normal, from which you can have the relation of ASHRAE tau alpha by tau alpha n is 1 plus B 0 times 1 by cos theta minus 1, and you have got the effective angles of incidence for the direct radiation in the form of a graphical representation, or the effective angle of incidence for the ground reflected radiation and the sky diffuse radiation, which are constants, they do not change with time, they are a function of the slope beta only, that is your theta g and theta d. So, one can estimate your tau alpha bar as per the relations which we have already dealt with in detail. So, like we have done for the liquid based systems, either you use the utility bills to get the space heating or calculate L space heating as UAH, that is the building heat loss coefficient multiplied by degree days multiplied by 24 into 3600 to make it consistent units. Then hot water requirement space heating, domestic hot water is mass of the water required multiplied by the specific heat multiplied by the water means temperature T m and the temperature at which the hot water delivery is required or desired. And of course, L loss from the tank is based upon the UA of the tank, either you can estimate or from the manufacturer specifications you can use it, and the temperature difference that is available for the losses will be T W minus the T surrounding, which may be different from the ambient temperature. So, L will be L S H plus L D H W plus L loss. So, that is what we have written in detail, each term contained. So, once again the system is valid for standard configurations, I am sorry, the correlation is valid for standard configurations like the 4-5 pictures I have shown schematically, and all the collectors are in parallel. Then energy delivery at or above 20 degrees C. So, the equation of f in terms of x and y is valid for standard storage, just like the case for the air systems, and standard load heat exchanger. This load heat exchanger was absent in the case of air systems, because when you are using space heating based upon an air system, you directly let the hot air go, the quantity being controlled by the temperature set inside the room and your desire. Whereas, in the case of water heating, there should be a exchange mechanism from the heat of the water to heat the air, which in turn goes to the rooms to keep it at a comfortable level of approximately 20 degrees C. So, this is valid standard load heat exchanger for a value of epsilon L C minimum by U A house equal to 2. Of course, epsilon L is the load heat exchanger effectiveness and C minimum is m dot C p minimum of the fluids on the two sides of the heat exchanger, and U A H is the building loss coefficient. Obviously, this is non-dimensional. There is a easy way of looking at these things. First of all, if I put a epsilon L C minimum and some delta T by U A H times some delta T, not that the delta T relevant for calculating the space heating load is the same as the delta T across the heat exchanger, but dimensionally one can draw some comfort that this is the ratio of the capability of the heat exchanger to transfer a certain amount of heat to the amount of heat that needs to be transferred. So, if you have a large heat exchanger, it can transfer the desired amount of heat with a low delta T, and if it is a smaller heat exchanger, it requires a larger delta T and hence a penalty on the heat exchanger effectiveness. And I shall recall also heat exchanger effectiveness within the conventional assumptions of your heat transfer analysis in heat exchangers. This can be written as m dot C p minimum times T C O minus T C I if m dot C p of the cold is less than m dot C p of the hot, by so I can write this in fact as cold by m dot C p minimum times T H I minus T C I. So, if m dot C p cold is the minimum, then epsilon L is given by T C O minus T C I upon T H I minus T C I. Alternately, if m dot C p hot is the minimum, you have epsilon L is T H I minus T H O by T H I minus T C I. So, the inherent assumption is the heat lost by the hot fluid is the heat gained by the cold fluid. This may not be in general true. Sometimes some books in heat transfer, they define the heat exchanger effectiveness as the desired effect, either it is the cooling of the hot fluid or heating of the cold fluid upon m dot C p minimum times T H I minus T C I. So, this is only to recall and make you little comfortable with this parameter. This is already known to us with the knowledge of heat transfer. So, if there is standard storage is not there, or the heat exchanger effectiveness is not the standard, just like we had done in the case of F chart method, the corrections have been given. X c upon x is actual storage capacity by the standard storage capacity to the power minus 0.25. This is valid in the range of 0.5 less than actual storage by the standard storage less than 4, fairly wide range, half of the standard storage to 4 times the standard storage. Similarly, if the heat exchanger is non-standard, the variable y is corrected to y c from the original y according to this equation, 0.39 plus 0.65 exponential minus 0.139 u a h by epsilon L C minimum. If epsilon L C minimum by u a h is equal to 2, this will be equal to 1, and this is valid in a range of 0.5 less than epsilon L C minimum by u a h less than. It is a pretty wide range for the epsilon L C minimum by u a h product, 1/4 that of the standard heat exchanger to that of 50 times that of the standard heat exchanger. So, now if you combine F air for an air based system and F liquid for a liquid based system have been correlated in terms of 2 non-dimensional variables x and y. These f's may be different, but it is only a functional notation, and if this is corrected for non-standard flow rate, and storage, this is corrected for non-standard heat exchanger and storage. So, you may be a little surprised why the flow rate does not come into the picture in the case of liquid, and heat exchanger does not come into the case of space heating. That we had already explained. If it is space heating air as it is used, and in the case of liquid system, the flow rate typically has less effect on heat transfer coefficient and hence ultimately on F dashed, the collector efficiency factor. So, the flow rate let us say 2 liters to 4 liters, or unless the range from laminar to turbulent flow changes, my heat transfer coefficients are pretty much in the same range. And more importantly, if you recall the expression for F dashed, the resistance is something like 1 by h, and h if it is of the order of 300, even if it becomes 600, 1 by h pi d I will be still small. Consequently, the flow rate of the liquid system does not make much difference in F dashed, whereas for air systems flow rate is an important thing, and the correlation is standard for 10 liters per second per meter square of the collector area. For other flow rates, we need to have the correction. So, that is the philosophy in providing a correction for the flow rate for air based systems, and such a correction has not become necessary for the liquid based systems, since the convection resistance in the case of liquid based collectors is quite small. So, the general need is also the third one. It is before we go to the next method, service water heating. Without saying that minimum temperature is so much, if you want desired at T W, mains temperature is T M, then simply F chart for liquid based systems is modified with x c being given in terms of the x as 11.6 a constant plus 1.8 times T W plus 3.86 T mains minus 2.32 monthly average ambient temperature T A bar upon 100 minus T A bar. So, you simply change the value of x to x c as given by this equation and use the F chart for the liquid based correlation, and you will have the solar load fraction met by service water heating systems. So, T m is the mains temperature and T w is the minimum acceptable hot water temperature. So, this is a slightly modified approach to that of the F chart, and then came the design methods, which is quite popular, little more general than the F chart method, which is called the phi bar F chart method. Main difference is between F chart and phi bar F chart is T minimum can be specified in phi bar F chart method. In other words, if you want energy delivery at or above a certain temperature T minimum, you can use phi bar F chart method. Interestingly, for some applications where F chart method is applicable, you can use phi bar F chart method, but not the other way around. So, now monthly load fraction is somehow should be similar to my x, y, and somehow I have to relate to T minimum. So, this is slightly modified and it is related to some x dash, a modified x, and the same as y, and this will give rise to what is called an x c bar minimum, which is, I will say, a non-dimensional critical level. Okay. And if you remember, very preliminary idea of the critical level was given, that if Q u is set equal to 0, the radiation falling on the collector for Q u to be 0 will be the so called critical radiation level. In other words, unless your solar radiation is above this critical level of IC, you will not have any useful energy delivered at the temperature desired. So, this Xc bar minimum will correspond to, we will spend considerable time on some monthly, and phi bar in general is the monthly average daily utilizability. We have also in a cursory manner introduced the concept of utilizability. This is nothing but solar radiation falling on the collector above the critical level to the total solar radiation falling on the collector. Okay. The general definition is how much of solar radiation is above the critical compared to the total solar radiation falling on the collector. Pictorially, if this is some sort of, it does not have to be smooth, it can be cloudy, etcetera, etcetera. This is minus omega s to plus omega s. This is the solar radiation distribution. It does not have to be symmetric if the collector is not facing south, and this is my IC. That is the critical level which we are talking about. Then if this is area A1, and this is area A2 under the line, if it is a single day, utilizability for the day will be area A1 by area A1 plus area A2. That is the solar radiation available above the critical level to the total solar radiation available. So, this concept can be applied for a month. If you want 5 month, I can say that 5 day multiplied by HT sum over the days by HT sum. This is a little more easy way of conceiving the definition of utilizability. What I am trying to do is, I am picking up the solar radiation every day above the critical level upon the total solar radiation falling on the collector in the month. This is also equal to phi bar. Numerically, it does not make any difference because it is a ratio of both. Okay. So, let us go to little bit about the critical level. So, my useful energy gain equation is Q u AC Fr times I t tau alpha minus U L into T I minus T A. For the sake of completeness and clarity, here I shall use the time factor delta t. Otherwise, you may not be able to calculate the critical level over a period of 1 hour integrated compared to the intensity at an instant. So, if you set Q u equal to 0, the critical level at that can be obtained by F r U L T I minus T A by F r tau alpha times delta t. So, if it is for a period of 1 hour, I will get it as joules per meter squared hyphen hour. So, with reference to the previous diagram, what we really calculated is maybe something like this. This is 1 hour and this is continued, and that is what I am saying as I c, or else this is I t. I t is each hourly interval, or minus omega s plus omega s. Alternately, you can call it G T, intensity on the tilted plane, to G C, the intensity of the critical level. Then this will be in watts per meter square, which is nothing but the ordinate over here. All right. We shall not go into this, because practical way of calculating with the utilizability will be with the hourly data, because that is the more or less the smallest time scale that is available to us. And I c minimum will correspond to F r u l into the minimum temperature at which my energy delivery is desired times delta T upon F r tau alpha bar, because I have already extended to T minimum, I have already extended to monthly average analogously, taking the average temperature divided by the average transmittance absorptance product over the month. So, from the definition, how do I write down? Now, my phi bar should be equal to summation over days over hours I t minus I c superscript plus by sigma I t over days over hours. That means, this indicates if I t minus I c is greater than 0, I t minus I c equal to I t minus I c, and if I t minus I c is negative, I t minus I c is set as 0, which means again with reference to the figure, you have imagine a wavy cloudy day where the solar radiation may be increasing or decreasing. If this is my I c, here is the contribution, here is a contribution, here is a small contribution here. This is negative, that it will not subtract from these positive things, it is treated as 0. In other words, practically speaking, if I give them A 1, A 2 and the total area beyond that. So, only A 1 plus A 2 by the area below the critical level, we have to take out the solar radiation. So, practically it means shut off the pump if I t is less than I c, okay, or T o of the collector should be greater than T I. This is where the practical difficulties I was mentioning will come in when you run a system on a system scale experiment or even on a component scale experiment. The control may not be able to shut it off exactly when TO is greater than TI. How much greater? It will have a bandwidth of 5 degrees or 2 degrees or 3 degrees, and consequently my shutting off or starting will not be exactly according to the mathematical control. So, the same phi bar can be rewritten over the days and the hours I t minus I c plus by sigma h t of the days, which is also one of the reasons why I am writing, though it is a very simple algebra, is now you will understand why we were worried about calculating h t bar, tau alpha bar, etc., in the beginning. So, if T minimum corresponds to x c bar minimum, that corresponds to phi bar maximum. That means, this is the solar radiation that will be available to you above the critical level, corresponding to the temperature at which energy delivery at T minimum desired. So, you can rewrite this equation. I will write down just the last one. Phi bar max should be equal to summation over hours over days I t minus I c min plus by n times h t bar. So, the emphasis is on the minimum temperature at which energy delivery, though it is the same correlation, you can automatically calculate whether you call it x c or x c bar minimum or I c or I c bar minimum. If you use the correct non-dimensional critical level x c bar, you will also automatically get the correct answer. But to be specific, we say T min corresponds to x c bar min, which yields phi bar max. Now, apart from the phi bar F chart method, if you have this phi bar, so q u in a month, I can calculate it as area F r times tau alpha bar n h t bar phi bar. We are not talking anything about the load fraction. We are not also saying whether this much of energy will be sufficient or not sufficient, whether something will be wasted or something will be stored, but the output from the collector, one can expect it to be the product of these quantities, and phi bar is to be found out. If we find out h t bar I know, tau alpha bar I know, F r is a collector parameter. So, methods to calculate everything is known except the monthly average daily utilizability. So, we shall reserve the calculation procedure for the monthly average daily utilizability, having understood that it is a ratio of the solar radiation available above the critical level to the total solar radiation falling on the collector. We will go ahead and see the correlation for the monthly solar load fraction in terms of the utilizability. Now, if If you recall the definition of the non-dimensional absorbed energy, F r tau alpha bar n h d bar by L is nothing but my y. So, if P bar max is the corresponding utilizability for the x c bar minimum, in a way this q u month, if I normalize with the load, I will have a product phi bar max y, which in one sense is the absolute maximum solar load fraction that the system can supply without other calculations. If all the energy delivered by the solar collector is going to meet the load, there are no losses on the pipelines, there are no losses in the heat exchanger or in the tank, then this will be the solar load fraction that will be met. So, in one sense, simple knowledge of utilizability can give you an estimate of what is a possible solar load fraction maximum. This is almost an ideal way of a number that one gets. So, again slightly I will digress before we proceed further with the definition or the simple correlation. What are the properties of this utilizability? I can define this phi bar for the month, I can define a phi bar for the hour in a month. Of course, as I have explained for the day also. So, this is in terms of summation over the days and hours. This will be summation over days I t minus I c plus for a particular hour. So, in other words, if you consider the hour 7 to 8, I will pick up the solar radiation of 7 to 8 for all the 30 or 31 days in the month, and how many of them are above the critical level, that will be summed up. The negative contributions will be ignored, that divided by of course, sigma I t over all the days for the hour. So, it is not the utilizability for several hours in the day, but it is the utilizability of all the days in the month for a given hour. So, if I know each hour's utilizability and you sum it up, and you will get the monthly average daily utilizability also. This has got a bearing with my clearness index distributions, which we discussed long time back, and again I will come back to that, because if the monthly average clearness index daily basis or hourly basis is a 0.7, 0.6 whatever, there will be days with a clearness index less than that number, and there will be days with clearness index higher than that number. So, some of the days will be contributing to the energy, in other words, I t will be more than I c during certain hours, or I t will be more than I c during a part of the day, and that knowledge will help us in calculating utilizability. I should be mentioning that this is a statistic that combines meteorology, rather solar radiation, and operating parameters. So, this takes care of your collector through F r u l and F r tau alpha, location, because my I t is location dependent, and T minimum is an operating parameter. Right. So, if some method of calculating this monthly average utilizability is known to us, or even the hourly utilizability is known to us, so that one can obtain the monthly average daily by summation over 10 hours or 12 hours whatever. And this is depends upon the collector parameters, the location through the radiation, and in fact the ambient temperature also, and the minimum temperature which is desired of the system. Again, the phi bar F chart method relates the solar load fraction to two variables x dashed and a y. Y is exactly the same as the one that we have written for the F chart method. Where F r is your collector heat removal factor, transmittance absorptance product, solar radiation monthly average daily multiplied by the number of days in the month, and the area of the collector upon the load. And the non-dimensional collector loss is slightly modified as x dashed equal to F r u l times 100 times delta tau, that is the number of seconds in the year month, by A c upon L. So, only difference is this comes in place of 100 minus T a bar. So, these symbols are explained over here. U and H d bar is all these things are known. So, the correlation reads F is equal to phi bar max y minus 0.015 exponential to the power 3.85 f minus 1 times 1 minus exponential minus 0.15 x dashed times R s to the power 0.76. Okay. This equation needs a bit of explanation. As we guessed or rather estimated rightly, your phi bar max y is the first term. If all the other nonlinearities in second and third terms are assumed to be small or 0, you will get simply f is, which will be the maximum, is phi bar max y. And this also contains R s, the standard storage by actual storage. Okay. Unlike in the F chart correlation, where the storage size is not explicitly present in the correlation, and x or y has to be corrected depending upon the storage is standard or different. In this case, that is included in the correlation itself. The other little uncomfortable aspect is this is a implicit relation. That is, your f appears on both left hand side and the right hand side. It can't be separated. So, this needs an iterative or trial and error calculation. So, compared to F chart, in addition to it taking into account the minimum temperature at which energy delivery is desired, this relation is explicit, and we need to calculate yet not known to us the monthly average daily utilizability. Appears to be an exciting parameter, which comprises of the statistics of the solar radiation and the collector parameters and the operating condition at which the energy delivery is desired. So, this is what I have already written over here, and standard storage I should tell you. (350 kilojoules per degree C). Now, in the case of liquid based systems, previously in the case of F chart correlation, standard storage is considered to be 75 liters of water per meter square of the collector area. This, if you multiply by 75, is approximately 75 kg, multiplied by 4.187, the specific heat is approximately equal to 350 kilojoules. So, the storage sizes are comparable, and this is standard systems employing for liquid based collectors connected in parallel. The collectors are assumed to be, this is an important, assumed to be operating at constant critical level. Okay. So, you have a situation here, the monthly solar load fraction can be calculated for a system delivering energy at or above a desired certain temperature. The additional parameter that needs to be calculated is the monthly average daily utilizability, but the limitations are storage can be taken care of, and but the critical level is assumed to be constant, yet methods are to be found out to calculate the utilizability other than detailed calculations through a correlation or some other simplified method if your critical radiation level is varying with time. Now, last but not the least, this correlation, we do not know anything about the heat exchanger, number 1. Number 2, we also have not explicitly considered or implicitly considered in deriving this relation the losses from the tank. So, you might wonder why the losses from the tank were not there in the F chart, nor I mentioned about the tank losses and the heat exchanger correction. Only correction for the size of the heat exchanger was there, because it was explicitly developed for different values of epsilon C minimum by UAH, whereas in this case as such this stands tank losses neglected, and an infinite heat exchanger. In other words, there is no delta T required in the heat exchanger. So, this is we shall stop now and continue with it in the next class.